Hello my dear crescents. Today we'll continue the electrostatics 3 part, and today we'll discuss the electric potential due to electric dipole. In a previous class we have discussed what is electric potential, that some amount of work required for bringing a unit positive charge from infinite to desired point. And in previous class we have also discussed what is the formula of electric potential due to single isolated point charge, and that formula was plus or minus beta into source charge magnitude divided by distance, plus sign for calculation of for positive source charge and minus sign for calculation of negative source charge. Today we will discuss the same problem, electric potential due to distribution of charge, that means for an ideal electric dipole. In previous class we have also discussed what is electric dipole. Dipole means at a two pole there should be two charges of same magnitude and opposite in nature. Ideal means magnitude of charge at each pole should be so large and dipole length should be so small. That means within a very small space, due to large amount of source charge, we can get the large amount of electric field or electric potential within a very small space. That's why it is known as ideal dipole. So ideal dipole means your 2L length is very small. Now we have to discuss the derivation of electric potential due to ideal dipole for three different cases. Case 1 for calculation equatorial position, and for case 2 we have to calculate at axial position. Then we will go for general derivation at any arbitrary point. Same three cases we have also discussed in the calculation of electric field intensity for ideal electric dipole. And derivation is very simple. You just follow this derivation and you do practice for easier in your exam. So first we will go for case 1 at equatorial position. Diagram part is very important. So systematic diagram should be done. First we draw the axis. It is represented by dotted line. This is axis, and this is a perpendicular bisector, that means equatorial position, and this is the center of the dipole O. Here the two charges of the electric dipole minus q and plus q, which is equated at A and B respectively. Usually we are taking the dipole length 2L, that means this length is L and this length is L. So our question is at equatorial position or perpendicular bisector position, or you may call it broadside position. That means in this line at any point we have to calculate the electric potential. So here P is our desired point. P is our desired point. We have to calculate, but we will solve our problem. How could we calculate the problem? Now basic criteria is you should know this is the point charge and this is the point charge. Separately we have to calculate the electric potential for minus q and plus q. Then we can algebraically add it, because electric potential is a scalar quantity. So before going to derivation, first you recall in previous classes what is the formula we have used for single isolated point charge. Plus minus beta is proportionality constant, source charge by distance. Plus sign is calculated for positive source charge. Keep in mind this is very essential. And minus sign is for calculation for negative source charge. Here you see the charge is negative and this charge is positive. PA distance is the same as PB. Let the distance is x and x, and from the desired point is situated at the distance r from the center of the dipole. So first we calculate the electric potential at the point P due to minus q. That is represented as VA. See, minus sign is here, proportionality constant, source charge magnitude is q, and the distance is your x. That's why minus beta q by x. Similarly, electric potential at the point P due to plus q, answer should be plus sign, proportionality constant beta, and magnitude of source charge is q and divided by distance. Plus beta q by x, here minus beta q by x. So total electric potential at the P is due to algebraic sum of the electric potential due to A and due to B. As I am telling, it is algebraic sum because it is a scalar quantity. That's why when you start the derivation, you should write VA plus VB. By mistake, you should not give arrow mark here. But in electric field intensity, we are representing arrow mark because electric field intensity is a vector quantity, but electric potential is your scalar quantity. Then you put the value. So answer is 0. So you should keep remember the at any point on the equatorial position, the electric potential is 0. That means at every point on it, potential is same. That means if you move any charge body on this line, there will be no work done because change in potential difference is 0 in this line. So total work done will be 0 if you move in this equatorial position of the electric dipole. So this is the case 1. We have calculated the electric potential due to equatorial position. Then we will go for second derivation, and second derivation is like that, and this is case 2. This is at axial position, or we may call it end-on position. Similarly, here diagram part is important. This is the axis of the dipole. This is your axis of the dipole, and you represented your dipole at minus q and plus q here, situated at the point A and B. O is the center of the dipole. P vector is the electric dipole moment. It's a direction along axis from negative charge to positive charge. And P is the desired point where we have to calculate the electric potential, which is situated at a distance r from the center of the dipole. Similarly, here how can you calculate the potential here? First we will go for minus q, then we will calculate for plus q, then we algebraically add it, so we will get our final result. Before going to derivation, we need the distance of the point P from the point A and distance of the point P from the point B. You just see the diagram. PA will be how much? This R and L. So it is R plus L. Similarly, PB is how much? PO minus OB, that is R minus L. So by using the formula V is equal to plus minus beta into source charge by distance. So at the point A, due to at the point A minus Q, and at the point P, calculation part will be, as it is source is negative, minus, and here for source charge positive is plus B, and this is proportionality constant beta and beta. Source charge is at Q and Q. As distance PA is R minus R plus L, that's why it is written as R plus L and it is written as R minus L. Now we have to calculate the total electric potential at given chosen point P. So algebraically we can write VA plus VB. You just see the simple mathematics. V value is written here minus beta Q by R plus L, and B value is written here beta source charge small q divided by R minus L. Beta and Q taken common out. First part is 1 by R minus L, then second part is minus 1 by R plus L. Then you took square R square minus L square. So first term will be R plus L, then R minus L, and R and minus are cancelled out, that is 2L. You just keep Q near to 2L and keep in square bracket. Why we are keeping this term together? Because it represents electric dipole moment. In previous class we know that is Q into 2L. So it is electric dipole moment. So at the axial position, the answer is beta P by R square minus L square. As we are discussing for ideal dipole means dipole length is very very small. That 2L is very small. If you take square, then that term will be again very small. That's why L square term is neglected with respect to R square term. So our answer is very similar to beta P by R square. This is a formula we have to keep remember. For ideal electric dipole at axial position, V axial is beta P by R square. That means V proportional to 1 by R square. But in case of electric field intensity, it was E proportional 1 by RQ. But here V proportional 1 by R square dependence, but intensity is 1 by RQ dependence. Now for calculation in SI system, in vacuum, we put the value of beta is 1 by 4 pi epsilon 0, and for electrostatic unit and CJ system, beta value is 1, so our formula will be P by R square. So this is the calculation at axial position, and this is also calculation for equatorial position. Now This is the general derivation at any arbitrary point. That means this is the axis of the electric dipole. This is the perpendicular bisector. But we are not taking the point at here and here. Just other position. That means at any arbitrary point, and chosen point is M here. You see the derivation. Simple mathematics is there. Just you follow it. OP, the position vector of the point M, let it is R vector. And this is the dipole moment, negative charge to positive charge along the axis. And this is the theta. Theta is the angle between P vector and R vector. And here OM vector is your R vector. Now how will you derivate it? Same procedure. At the point M, first you have to calculate electric potential due to minus Q. Then we have to calculate electric potential due to plus Q. Then algebraically we will add it, and then we will get our final result. Before going to that, we have to some geometry constructions part. You just follow for the easy process of our derivation. What? Actually, I am interested to calculate MB and MA. For that, I draw a perpendicular B dash here and A dash here. As this point M is very far from the point O, MB is nearly equivalent to MB dash. Exactly not equal, but nearly equal, because this distance is very small. So our aim is, we have to calculate MB dash, so it will help is same as its value is MB. Similarly, we have to calculate MA dash, this also very similar to MA. So our aim is, we have to calculate MA, and our aim is, we have to calculate MB. For that purpose, we have drawn two perpendiculars here. As it is theta and this is opposite angle, this is also theta. You just small two right angles are there. First we will go from O, A dash right angle triangle. If we will use the triangle law, then OA dash will be OA cos theta. Similarly, OB dash will be OB cos theta. I have written here in OA triangle, OA dash will be OA cos theta, and value of OA is L, that's why it is L cos theta. Similarly, OB dash is L cos theta. Now our aim is, we have to calculate MB, but as point M is very far, or this distance is very small, that's why MB is nearly equivalent to MB dash. Not exactly equal, nearly equivalent. And this is only applicable if the distance is very far, that means for ideal dipole. OM minus, again you see, MB dash. You see the diagram. How can you calculate MB dash? MB dash means OM minus OB dash. OM is your R. OB dash is your L cos theta. So R minus L cos theta is MB dash. Here written MB dash is equal to OM minus OB dash, that is R minus L cos theta. Similarly, MA is OM plus OA dash. OA dash is L cos theta and this distance is R. So it is R plus L cos theta. Now we have to calculate separately VA, that means electric potential at the point M due to minus Q, and VB, electric potential at the point M due to plus Q. As it is, source charge is negative, minus sign is here, and source charge is positive, plus sign is here. And same proportionality constant beta and beta, same source charge Q and Q, only distance is different, MA and MB. We are putting the value MA, that is R plus L cos theta, and the value of MB is R minus L cos theta. So you should remember the value of VA is minus beta Q by R plus L cos theta, and VB is plus beta Q by R minus L cos theta. Now by algebraic law of addition, the total electric potential V is equal to VA plus VB. Put the value VA and VB here. Then you taken common beta Q outside. So first term will be 1 by R minus L cos theta. Then second term will be minus 1 by R plus L cos theta. In LCM, that will be R square minus L square cos square theta. First term will be R plus L cos theta. Then minus R minus L cos theta. If you will expand, R and minus are cancelled out. L cos theta and minus plus L cos theta. This one is your 2L cos theta. Now beta kept outside, Q into 2L. I have written together, and this is your cos theta. Why I have written together Q into 12? Now in previous class you know that this is the formula of electric dipole moment of the electric dipole. So it is P and this is cos theta r square minus L square cos theta. For ideal dipole, as 2L is very much less than R, so L square cos theta is very much less than R square. So if we will put here, this term is neglected with respect to R square term. So you see carefully that term is R square, L square, R square 30 is neglected due to ideal dipole. Now the general formula is V is equal to, I am putting beta here 1 by 4 pi epsilon 0 for SI system vacuum. So our answer is V is 1 by 4 pi epsilon 0 P by R square into cos theta. This is the general formula. If you are interested from this formula, if in exam question comes first to derive this formula, then we will go for case 1 and case 2 that today we have discussed. In this class today this is our case 1 and this is our case 2. First you see the diagram. This is the any arbitrary point M here. For case 1 means equatorial motion, that means point M will be to this side. So theta will be 90 degree. When we will come to axial position, it will close down, the theta will be 0. So this is theta 0 and theta 90 degree. For equatorial position, if we put theta 0, then electric potential will be 0 because cos 90 is 0. For axial position, if you theta 0, so your answer is 1 by 4 pi epsilon 0 P by R square. So this is the way how we derive the electric potential due to an ideal electric dipole at any arbitrary point. Then we also derive the equatorial position and we also derive the axial position. Very simple mathematics is there. If you do practice once times, then there is no problem in your exam. Thank you all.